to this tutorial of Helmholtz Resonator with flow, interaction of flow and acoustics. My name is Ali and I'm an instructor at Asyut University. We're gonna say what is Helmholtz Resonator first. The Helmholtz Resonator is a part of exhaust system, as we can see here. We can put it on the duct or something like that for removing some part of noise, and we have such a transmission loss as the flow goes to the resonator and then come out. The presence of flow change in the transmission loss depends on the flow coming into the resonator. In this tutorial, we will gonna study the transmission loss of the resonator for different flow inlet. First, we're gonna say how we can do that in comsol. Modeling of air acoustic and comsol multiphysics require three things. First, we're gonna solve the flow safety domain. The fluid domain, we make a safety mesh, and then we solve it in an unsteady safety competition, or maybe sometimes stationary, depends on our study. And then we have a safety solution of BV and rho. In another part, with a CAB model, we made an acoustic mesh. And then we map between the safety solution on the safety mesh on the acoustic mesh. So because we made the acoustic mesh less dense than the safety mesh will be more dense. And then having the values on the acoustic mesh, we're gonna solve a linearizing Navier-Stokes equation as we do some permutation, like you are simplified Navier-Stokes equation into a linearized form. So Navier-Stokes equation will be in only the acoustic pressure and acoustic velocity. And then we can solve the solution here to have acoustic radiation. So we have three things: safety study, mapping study, and linearizing Navier-Stokes equation acoustics domain. So we're gonna see here how that could be. The acoustic model and comsol have a full Navier-Stokes equation for solving safety. And then by linearization, make it as acoustics. As we say, the total velocity of any point, it equals the reference value of the velocity, and then the perturbation velocity forms the acoustic flow field. And then after doing that, we transform the full Navier-Stokes equation into linearized form of Navier-Stokes equation. If we just make the flow velocity equal 0, we have thermoviscous acoustics. This is a model inside comsol. If we just make it like ideal, we can have a linearized Euler. And for linearized Euler, if we make it adiabatic, so we have a corrected wave equation. If we make it irrotational, we have a linearized potential flow. And so it depends on your study, what you want to do. If you have an adiabatic flow, if you can model an ideal flow outside solid domain, it depends on your model. If you also have heat transfer flow, velocity is really small, so that's why you don't like to get it in the acoustics field. And then if we don't have the two things, the flow is ideal and at the same time it doesn't have a heat transfer, so we go to pressure acoustics, various loss fluid models. We have a porous model, narrow region model, and complex value model. Today in our tutorial, we will go from the full Navier-Stokes equation to linearized Navier-Stokes equation. Okay, we will not talk about Euler or thermophysics, just only the two first things. So the geometry of our model consists of the resonator himself is a circular duct, and here a circular duct too that the flow goes on with UN with different values of flow. And we have also a background acoustic field. We put it as a wave inside the flow. So we're gonna see the interaction between the background flow field and the value of inlet flow. And for here we put a PML, perfect matched layer, in the inlet and outlet flow for removing the reflected wave. Okay, so we cannot have a reflected wave out from outside the domain into the domain. The mapping between safety and air acoustics is really important because we in the safety we need to have a more dense safety mesh, but in acoustic we didn't have we have such a less dense, so we need to map between this safety mesh to acoustic mesh. So we locate every point here on every point here, and we take the results after CFD study. So we can like easy doing the study here in a acoustic mesh for less computational costs. An example for the acoustic mesh here in this tutorial and the CFD mesh. We can see the CFD mesh is almost quadra elements, but only in the part of the resonator is like tetra. But here we can find it's a lot of tetra here. Just only the BML, the perfect matched layer, is quadra, and we can see also them here like the elements are really smaller than this. We can see here in acoustic mesh. After solving, the results will be like the velocity distribution here and the velocity turbulent viscosity, and then we make the mapping study, and then we compare between the values of velocity from coming from CFD and the values from coming from mapping study, and then also we do that for dynamic viscosity. After that, we solve a linearized Navier-Stokes equation, and then we can see the acoustic pressure in the flow with no flow, and the acoustic pressure with like 0.01 or 0.05. Finally, we have the transformation law that we wanna like for the three cases, and Mach number 0, Mach number 0.05, and Mach number 0.1. Okay, so let's see how we can do that on comsol. Thank you.
We begin the model by model wizard. In the model wizard, we choose 3D. In the 3D, select physics 3 is fluid. We selecting fluid flow, single phase flow, and then turbulent flow. From the turbulent flow, we select turbulent flow SST. We have key epsilon model, key omega model, key low realizable Spartan Malers. We will choose key omega SST and then press study. The study can be stationary with initialization or time dependent. We will choose stationary, global definition, parameters, and then we should have the parameters. Select here, load from file. Then we have the parameters. Then we go to geometry. In the geometry, click cylinder, and then in the setting window, cylinder, look at the size and shape, and then choose the radius to D main over 2. Choose the height to Ln plus L out plus 2 over. So we go to Z here and we type minus Ln minus L PM click to expand the layer name, so it's LBML, perfect matched layer. We remove layer inside and we put layer in top and layer bottom, and then build selected. So we have here, we have layer in bottom, we have layer on top with LBM thickness. So this is cylinder 1. We have another cylinder 2. In the cylinder 2, type here in the radius, the neck over 2, the height, which 1.2, and L the neck, and then look at the position. In the X field, we put D main over 2 minus 0.2 in L neck. For the axis, we locate the x-axis. We have that right now here. For cylinder 3, size and shape D raise on over 2. For the height, L raise on. In the position, in the X field text D main over 2 plus L neck. And then for the axis, we have the x-axis. It's for the resonator. So we have the resonator here. By D resonator, L resonator, X main over 2 plus L neck. Then we have cylinder. This cylinder for the source, the same as D main on the radius over 2. And its height, we called it L source. And it will be in a z-axis. The position is minus Ln. We build the selection. We have here the L source. And then cylinder forces. Then the cylinder for this is also D main over 2. For the inner side here, we have the D main over 2. In the high we have 0.2. In the position it's minus 1 point set. And then we build selected. So we are just like this position will have different mesh. So that's 4. We made it different. In the geometry toolbar, in the boolean and partition, we choose partition domain. The object cylinder 2 select domain 1 only. This domain. From the partition, we choose extended faces. We select 12 and 15. In cylinder 1, repair tolerance, we select relative and then build selection. We go to the wireframe. See here, this is 1 and this is 2 there. We have to choose the main here, and then we select that domain. We're gonna delete it. So it's deleted. I'm gonna make a union in the boolean. In the boolean and partition, we choose union. Okay, in union. Click in the graphic window and then Control A to select all objects. We're gonna select cylinder 1 to all objects. Okay, build selection so they become one object. Okay, we will make a work plane to cut the geometry into 2 sections. Geometry toolbar, click here, work plane, and then the setting window for work plane. In the plane definition, we choose ZX. It's ZX plane. Okay, we build selection. Also click partition object here, another partition object. In the boolean and partition until 1
unit 1 with the work plane. We're gonna make it 2 partitions, and we then build. Okay, it becomes to be 2 here. Then we have delete 2. Okay. Right click in geometry 1, choose delete entities. In the setting window for delete, or locate the entities to delete, and then choose the main. Okay, yeah. You select 10, 12, 9, 14 to delete. So 2, 4, 6, 8, 9, 10 and 12, 14, 16, and then we built selection. So now they are deleted. Okay. So we're gonna have a symmetry. We're gonna have an explicit. So in the definition, we're gonna have an explicit. In the setting window for explicit, look at the input entities. This is input entities. From the geometric entities, leave a list, choose boundary. So we're gonna make this boundary as symmetric boundary. We will put symmetry here, and then we're gonna make a new explicit. In the boundary, we're gonna choose outside. Only 1, 4, 7, 10, 13, 60, 21, 2, 3, 4, 5, 26. We're gonna remove this 26. Okay, 28. We're gonna type walls. So we have 2 definitions. Okay. And then we add material. Add material from library. Okay, we're gonna have here built-in. Go to air. Okay. So we click add to component 1. We're gonna have air like that added. In the home toolbar, click add material. To close add material window.